Hello, folks. Welcome to your lecture, originally scheduled for Thursday, January 29th, now being watched, hopefully whenever you can watch it. There are some lectures, there are some video lectures just built in here where I'm going to be doing them down the line. This was not intentional. I had some childcare issues that could not be surmounted. I don't want to skip one of these important lectures, so we're going to go ahead and do it this way. And hopefully that works for everybody. We'll be back to get started on Tuesday. So today we're going to continue with our kind of general evolution ecology treatment, going into some issues, some things that are going to be variably important going forward. So phylogenetic nomenclature is how we name the groups that we recognize, right? Name the higher taxonomic groups. That's going to be a pretty unfamiliar approach to pretty much everybody, and it tends to be a subject that's pretty difficult for most people. So please do the background reading on that, and I'll give you some help on how to do that. Reconstructing phylogeny. So this is another one that is potentially hard. Some people get it really easily. There's a quantitative aspect to it that you'll want to make sure that you get. And then reconstructing ancestral states. So this has to do with looking at a group, a clade like the mammals, and asking, okay, did the ancestor of mammals have 3 small ear bones, things like that. And then I'm not sure if we will include this ecology terminology in this particular lecture. I'm going to see how things go, but just to warn you that we might finish up with that. And that'll just be some very basic terms that we're going to be using, similar to those terms at the end that, dorsal, ventral, proximal, distal kind of thing, where you probably won't be tested specifically on these terms, but you will be expected to know what they mean. Before we get started with the main lecture today, I wanted to give you some help because there's a couple of these issues that I worry about people doing well on that we've talked about recently, and one of them is the structure of phylogenetic trees. Please do that kind of supplementary reading so you can try and get a better handle on it. This is an actual test question from the first test the last time I taught this course. And it's a pretty typical one. There's 2 aspects to it that I'll show you. So we show you a set of phylogenetic relationships here. Then ask, given those relationships, which of the following is true? Stolidobranchia is equally related to Molgulidae and Apendicularia. Stolidobranchia is more closely related to Molgulidae than to Apendicularia. Stolidobranchia is more closely related to Apendicularia than to Molgulidae. Vertebrata's relationships, more than one of the above or none of the above. So this is getting you to understand what it means to say things are related to each other in the context of trees. This is a set of groups that are going to be unfamiliar, but the point is not to know what the relationships are. The point is to be able to read the trees. So if we look at these options here, look at, if you're looking at the tree, look at the second and third words from the bottom. So the Molgulidae and the Stolidobranchia. So those things form a clade. They're the closest relatives to each other on that tree. So option C, where we say, for example, we say Stolidobranchia is more closely related to Apendicularia than to Molgulidae, isn't correct. Answer B, where Stolidobranchia is more closely related to Molgulidae than to Apendicularia, is the right answer. And I would encourage you to go through those other answers and kind of see why they're wrong. That's the only right answer among those. Here's another. Do the above evolutionary relationships or phylogeny conflict with those shown before? And this is another just tree reading question. And what we have, that top tree is clearly from a publication that I just screenshotted it from some PDF. And the bottom one is just a tree that I put together that is a much more kind of, ball and stick, no pretty pictures kinds of things. And so this one is, one that's difficult for people. You have to ask, if you were to sort of strip these trees down to only the taxa they have in common, are we seeing the same relationships? And the answer is that yes, that tree at the bottom is showing the same relationships among the shared taxa as the tree above. The homology is another one that people get tripped up on, and I can't help but think some of the tripping up has to do with like University of Google, because I said that's an approach that's probably going to lead you astray here. So this one, which of the following is the best example of homology? And this is a common way that I ask questions on tests, is to give an example and ask whether the example fits with the concept. I'm generally not going to ask you, what does homology mean? So here are options. Cats and dogs breathe air, birds have wings, bats have wings, humans have mitochondria, plants with chloroplasts. A set of taxa are members of vertebrata, or a different set of taxa are members of vertebrata. The answer here is A. And I think it throws people who don't have a strong understanding of the concept to just think about the idea of something as simple as breathing air and having this supposedly complex concept in biology applying to it. The last two questions, D and E, have nothing to do with homology. They're just taxonomic questions, but sometimes people associate homology with particular taxonomies. And, B is an example of, classic example of convergence, not homology. And then C is comparing two things that are different. So homology doesn't apply. All right. If you jumped at choice A as soon as this was up there, then you're probably in pretty good shape. Okay, now getting to our subject matter for today. Phylogenetic nomenclature, specifically what's the basis for taxon names, how are taxon names defined. So let's take the name Tetrapoda. That's a name that's probably familiar to everybody before you ever took this course. Tetrapods, right? So how do we define that name, right? If we're saying Tetrapoda is a thing in biology, what is the definition of that? Well, here's one potential definition, and this is one that's been used for this sort of thing, is basically come up with a list. And this could be a list that includes everything we currently consider to be Tetrapoda. The problem, of course, with that, even though it actually resembles some fair amount of current practice, but the problem, of course, is it's like making a map with a scale of 1 to 1, right? You're just listing things. You're not allowing for things that are going to be named in the future, and so on, and so on. All species with 4 limbs is probably the definition you would think of. It's probably the definition that you would get from a Google search. So let's think about that as a real definition. All species with 4 limbs. Tetrapoda is a thing that includes all species, for which all species with 4 limbs are in. Now, discounting, ideas about like insects and things like that, we could qualify and say all species with 4 limbs and a backbone, something like that. There are things that everyone agrees is a tetrapod that don't have 4 limbs, right? Snakes, for example. And, you ask someone who ascribes to this kind of definition, they say, oh, well, yeah, snakes are an exception, but they're still tetrapods. And, in biology, often when you start to try and make excuses for exceptions is when you realize there's something wrong with your concept. Because it doesn't work, right? It's not the definition of what we mean when we say Tetrapoda. The approach that you're going to learn today of phylogenetic nomenclature takes the form of this last option. All species more closely related to humans than to fish. Something like that is your tetrapod. That's not a formal definition. It's not a real one, but that's the form of it. Notice what it's doing, what it's identifying. It's specifically referencing relationship. And really that's what we mean when we talk about tetrapods. We're talking about an evolutionary group, a clade. So why does our standard definition that has to do with traits, 4 limbs, have these exceptions? No, we need to be defining groups in terms of how they're related to each other. This distinction is quite similar to that one that I presented earlier of species concept versus an operationalization of that concept. And the way that this biologist Tim Rowe refers to it is a definition versus a diagnosis. A diagnosis is a list of traits that help you to identify what you're looking for, that delimit the group. A definition tells you what the group is that you're looking for. So let's read this quick paragraph here. Mammalia may be defined as comprising the most recent common ancestor of living monotremes and therians, and all of its descendants. Thus, if an organism is born to a mammal, it is by definition a member of Mammalia, regardless of whether it has hair, mammary glands, or any other character commonly associated with mammals. This is an important paper, and it's one that I'm going to give you to read, although it is one that will also give you a lot of advice on how to read it. But the tree on the right is showing these multiple groups that have been called Mammalia by different, especially paleontologists, but all kinds of taxonomists. And within the paper, he goes through, each of their kind of what they call definitions, but were actually diagnoses. So list of traits where mammals are something that has only one bone in the mandible, or whatever. Okay, so this new way of thinking about taxonomic names, higher level taxonomic names, originated with a set of workers. Tim Rowe on the last slide is one of them. But the ones who really championed it and developed it were Kevin de Queiroz and Jacques Gauthier. De Queiroz, the longtime herpetologist at the Smithsonian, and Jacques Gauthier, paleontologist at Yale. They had a couple earlier papers, but this one called Phylogenetic Taxonomy from 1992 is the one that really has been cited 900 times or something. And well, let's actually just read this this section quickly. So, during the century following the publication of Darwin's Origin of Species, biological taxonomy waited for the revolution that should have followed upon acceptance of an evolutionary worldview. Although the principle of common descent gained wide acceptance early in the era, it assumed a largely superficial role in taxonomy. Pre-existing taxonomies were explained as the result of evolution, and evolutionary interpretations were given to long-standing taxonomic practices. But the principle of descent did not become a central tenet from which taxonomic principles and methods were derived. So hopefully you can see how that passage influenced my treatment of the history of systematics. If you can kind of draw that link, you'll be in pretty good shape. Another just important passage from this. Taxa are named entities, generally named groups of organisms. Under traditional interpretation, organisms belong to taxa because they possess certain characters, organismal traits. By contrast, taxa and phylogenetic taxonomy are historical entities resulting from the process of common evolutionary descent. That's the whole idea right there. That's the revolutionary part. Very simple. Don't get tripped up in this shift from phylogenetic taxonomy to phylogenetic nomenclature. Phylogenetic taxonomy is just a slightly sloppier name for the same thing because we're specifically talking about rules for naming groups. When we're talking about rules for naming groups, remember, we're talking about nomenclature. So they shifted to talking about phylogenetic nomenclature. All right, so what are the rules for de Queiroz and Gauthier's phylogenetic nomenclature? The first rule is utterly uncontroversial today. Maybe as recently as 30 years ago it was not, but today everyone agrees that the higher level groups you want to name should be clades. So remember we talked about monophyletic, paraphyletic, polyphyletic. I mentioned that monophyletic or clades is the important one. This is one of the reasons. So we recognize groups like the one on the left showing reptilia. We don't recognize, the middle old-timey reptilia or the hemothermia, birds and mammals together on the right. So the other part, the part that is difficult for people, is that you define your taxon names in terms of evolutionary relationship. So instead of, what is a tetrapod, something with 4 limbs and a backbone, what is a mammal, something with hair or fur and mammary glands, no, we're defining these in terms of evolutionary relationship. We're going to talk about 2 flavors of these names. There's actually multiple other kinds, but these 2 are the most used, and we'll only worry about them for the purposes of this course. One of them is called a node-based name. because it refers to the point right when one of those dichotomous splits in a tree occurs. More recent work often calls it a minimum clade name, and hopefully you can see why as we kind of develop this idea. These names take the form, the syntax, of the most recent common ancestor of X and Y and all its descendants, where X and Y are taxa, often species, but they could be already named higher groups. Remember, when we're talking about common here, we're talking about shared. Give you an example of this. The most recent common ancestor of crocodiles and birds and all its descendants is a group that we call Archosauria. So, this group right here. You take the crocodile clade, modern crocodiles, and the bird clade, and you follow them back in time in their evolutionary lineages, and you get to the last point when they shared an ancestor. That's the most recent common ancestor of crocodiles and birds. Then you add on that and all its descendants. So you're taking that point and you're saying everything that evolved from that, right? And that allows, not only for including all of the crocodilians and the birds and the other dinosaurs as well, but anything that gets described in the future as a crocodile or a bird is a member of Archosauria, not because it has feathers like a bird, but because it's a relative of birds. Another way to say this term, the node-based term, is to say Archosauria is the smallest clade that includes both birds and crocodiles. Think that through and think how those two ways of saying this are identifying the same groups, the same species. And if you can see that connection, that is a positive sign. All right, the stem or branched-based style of name, or also called a maximum clade name. This takes the form of all species more closely related to X than to Y. Again, where X and Y are taxa. Let's look at an example. All species more closely related to crocodiles than to turtles is a definition of the name Archosauromorpha. So you can see where that is similar to the name Archosauria, but you should also see where it's identifying a different group. It's not just identifying everything that comes from that split between birds and crocs, it's also identifying the branch that leads up to it. Okay? So you should be able to see how the node-based name and the stem-based definition are identifying overlapping but different sets of taxa. So here's just a circle around that group. Another way to say that, when we think of it in terms of maximum clade, is Archosauromorpha as the largest clade, including both birds and crocodiles, but not turtles. Again, if you can see how the grouping identified there is identical to the grouping that is identified by the stem-based form, then it's a positive sign. You might be asking why there are two kinds of names. And actually more than two kinds of names. This is an excellent question, and it's a perfectly reasonable question. Basically, these two kinds of names are meant to correspond to different concerns of biologists, or different concerns of taxonomists. So there's a lot of taxonomists, like me, who do a lot of taxonomy, but it's really exclusively on extant forms, so forms that are living now. There are a large group of taxonomists called paleontologists who work a lot with extinct groups. And so when so basically the two kinds of names, node-based corresponds to specializing in extant groups, and stem-based corresponds to including also extinct groups. So it just makes the statement I just said. Groupings focused on extant taxa. A nice name that you should learn for this is the clade that includes the most recent common ancestor of some set of extant forms and all its descendants is called a crown group. All right. So, for example, the crown group Mammalia includes only the most recent common ancestor of all the extant mammals and the descendants of that. So we'll learn about mammal-like things that branched off on the way up to mammals after the split with reptilia. And these are included under a stem-based approach. So stem-based naming is used to include fossil forms that branched off before the crown group diversified and that people want to kind of associate with that group. So Synapsida is a really well-recognized, well-known stem-based name for the species that include, or for the clade that includes all the extant mammals, but also the things that branch up on the way to mammals. So, cynodonts, Thrinaxodon, these things that are sometimes misnamed mammal-like reptiles, Dimetrodon. So we'll look at these. But this distinction, again, if you're kind of getting this, why, the thinking there, why that's, justified to think of those two different ways, then that's good. Okay, let's finish up this section on by contrasting the Linnaean system. So that's Carol Linnaeus on the left, and phylogenetic nomenclature represented by Kevin Nicaros on the right. I'll warn you that my treatment of this is going to be very much an originalist treatment of the Linnaean system. So people have tried to tweak and twist and turn the Linnaean system and try to use it for naming phylogenetic groups even today. I would argue, and the phylogenetic nomenclaturists would argue, that they haven't been successful, but just so you know that that's still a process that's happening. Certain of the elements that I'm assigning to the Linnaean view are not held by everybody who tries to use Linnaean names today. So let's start with what groups are actually nameable. So what are allowed things to name in terms of taxonomy? Phylogenetic nomenclature is very clear that one of its tenets is that you only name clades, you only name evolutionary lineages. In the Linnaean system, as originally formulated, clades could be named. Even after evolution was recognized, though, you could still name groups that included you could still name groups that included groups outside of some particular clade, or that excluded parts of a clade. And this is where your old-timey reptilia comes in, right? Where reptilia is all the things that we commonly think of as reptiles, but not the birds. That would be, this paraphyletic group that no one recognizes now. Problem with this is that kind of once you open that door to, allowing these other kinds of groups, it's not clear which other groups are allowed. If you allow everything, then, you're kind of not going to have arguments to get anywhere. And also along those lines, something like putting birds and mammals together, for example, because, their endothermy is so important. That's a consequence of our human perception of what we find to be important. That's not an evolutionarily significant part of the history. Okay, so I'm putting these two together because they're really similar, and there's ways to think of them as the same kind of issue. The original basis for phylogenetic nomenclature was clearly evolution. That's your first principles. You're saying, okay, evolution's the basis for everything in biology. Let's come up with a taxonomic system that works with that idea. In the Linnaean system, you are clearly, originally, trying to show what God was thinking, and the purview that when you're trying to learn about God by using the natural world is called natural theology. Talking about the phenomenon to be explained, phylogeny in the case of phylogenetic nomenclature, and then in the Linnaean system, your purview is natural theology. What you're trying to show is, the Creator's intent. What was the Creator trying to show? Why did the Creator choose these things as species? And the issues with this really address a real kind of science versus supernatural dichotomy. And, there's just not, science doesn't address things that are supernatural. It can't. It needs regularity. It needs some kinds of laws. It needs, not absolutes, but it needs things that are repeatable. And, that the other idea being that there's, and then, this is along those lines, just that there's no really good God model. And, this is a sort of Lord works in mysterious ways. A big part of belief in God has to do with belief in God, right? It's a matter of faith. None of these ideas have anything to do with whether there's like a God exists or not or anything like that. That's a different kind of thing. This is just saying that it's hard to have a taxonomy reflecting the supernatural because of these issues. All right, criteria for group membership. Mammalia, if you're going to be a mammal, it has to do with whether you're related to mammals. In the Linnaean system, it has to do with whether you possess key traits. So, strictly then, if some naked mammal evolved, then strictly it would cease to be a member of Mammalia, right? And the problem with this, of course, is the exceptions thing I talked about. Snakes as tetrapods, and then just which traits to focus on. We're focusing on traits that as humans we're noticing, but there's no reason that there's anything, that the special thing about being a mammal is fur, for example. Okay, and then the categories of names. Specifically, phylogenetic names are unranked. And that's easiest to understand by contrasting it with the ranked Linnaean system. Kingdom, phylum, class, order. These things have a particular they're a particular size of box relative to the other things. There are phyla that fit within the kingdom, and there are class which fit within the phyla. In phylogenetic nomenclature, you're just naming clades, and you don't run into the problems of superfamily, subfamily, subfamily, that kind of thing. I will finish this section just talking about a couple compromised taxonomic systems, because it's worth recognizing that there's still, I wouldn't say a very vocal faction, but certainly a fairly active faction that still tries to reject phylogenetic nomenclature. First one I'm going to talk about isn't used anymore, but it's a good example of this. There was something called evolutionary taxonomy that was championed by the great evolutionary biologist Ernst Mayr. Ernst Mayr, of course, believed in evolution and believed that there was an evolutionary pattern, but was skeptical of our ability to reconstruct those relationships. And not just that, he also thought that, even though he recognized phylogeny, he didn't recognize it as it should be the basis for taxonomy. He was saying we should be naming groups that have traits that we think are really important. So, your reptilia with sharing the ectothermy and the scales and all this, and that being separate from birds. And this system specifically used rank names. Nowadays, there's a lot of people who name clades, just like in phylogenetic nomenclature, but they tend to use Linnaean ranked names. This is tricky because often, the phylogenetic system isn't specific necessarily about the suffixes used. So whereas in the Linnaean system, something ends in an AE, DAE, Mantelidae, Rhonidae, Buffonidae, it's a family, right? The phylogenetic system doesn't care about that, but it does sometimes co-opt these names so that it doesn't make things really unfamiliar. And that can be kind of confusing because some people are doing this as, okay, I'm just going to use this familiar name, but I'm following all the tenets of phylogenetic nomenclature. There's some faction that does that and still looks at the group they're naming as in some sense just this, list of taxa. Okay, I think that's a good point for us to take a break, and then we'll come back and look a bit at phylogenetic analysis.